This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. A very good day to all joining our session today. Welcome to the AI for Good webinar. This is a challenge finale, and I'm very excited to be given the platform to moderate this session. So my name is Thomas Bascolo from ITU, International Telecommunications Union. And in today's finale, I'm very happy to introduce 3 problem statements that we're going to give awards today. We have at environment QoS prediction, network traffic scenario prediction, and SDN security. And this is part of the 4th edition of the ITU AI Machine and 5G Challenge that we started in 2020, for some of you who doesn't know. And for this problem statement, before we begin the presentations, I would like to introduce our speaker, distinguished speaker, who is going to give opening remarks, Dr. Tian from ZTE. And I would like to welcome you. Thanks for making time to be with us today and give opening remarks. The floor is yours.
Thank you. Thank you, Thomas, to give me the floor. So, ladies and gentlemen, esteemed participants, respected judges, and who have come together today with a shared passion for technology and innovation. So, good morning, good afternoon, and good evening. As a consistent contributor to these great AI for Good events, it's both an honor and a privilege for me to represent ZTE to inaugurate this AI ML challenge focused on the network traffic scenario prediction, QoS prediction, and security issues. As our digital world's burgeons, consistently reshaping the fabric of our societies, one thing becomes abundantly clear. So the data is the lifeblood of this transformation. And just as with any circulatory system, predicting and managing the flow is crucial. For example, predicting network scenario traffic, for example, it's not just a technical challenge. It's an economic, social, and strategic endeavor. So the precising of our predictions directly affects the user experiences, the cost efficiency for operators, and the smooth functioning of our social economic systems. So this is why the magic of AI comes into play. With its power to analyze vast data sets, learn from patterns, and make predictions, AI stands as our most promising beacon in addressing the network challenges of tomorrow. So in this challenge, we are very happy to see a good variety of participants from more than 100 countries, with both industry and academia players, not only proposing innovative algorithm and technology capable, but also solve practical solutions verified in real-world networking environments. So in conclusion, I would like to extend my gratitude to all participants for their dedication and time committed to this challenge, as well as our judges and staff for their relentless efforts. And I would like to also congratulations to the winners of this challenge that versus novel ideas and technological breakthroughs. Together, let's contribute our wisdom and strength to the future of AI applications for good for all. Thank you.
Thank you so much for your kind words, and we are really appreciative to ZTE, who has been with us for all the 4th editions. Since 2020, we always have a program statement from ZTE in the competition, and thank you so much for being part of this interesting endeavor, being part of the competition, being part of the network. At this point, I would like to give a quick overview of the competition, how we have run the challenge until today, and especially these 3 problem statements. So I would like to share my screen. So we have, as you already know, in this finale, we have 3 problem statements: MAT environment, automotive QoS prediction, that was proposed by Fraunhofer HHI, intrusion and vulnerability detection in software-defined network, SDN security, that was proposed by ULAC Communications from Turkey, and network traffic scenario prediction by ZTE. And so this is a quick overview. We have the background, the participation submission, and of course, we would like to invite you to submit your solutions to the ITU journal. So, when we started these problem statements, they started at different times. So this just gives you an overview of how we have handled an overview of the timeline of how we have handled the competitions, the different 3 competitions. We started around February to curate, and some opened around May or June and closed in either September or October. So this is when we finalized. And then from September or October, we requested for code and for presentations, reports, and of course for participants to create their GitHub repos. So we also have GitHub repository of the code, reports, and the PowerPoint presentations. We thank all of you who worked hard to make this a reality. And just in terms of people who made this a reality, we have here a number of hosts of problem statements, various problem statements in the 2023 ITU AI and Machine Learning 5G Challenge. And I have highlighted the 3 that we are finalizing today. So we have ZTE, Fraunhofer, and ULAC, who are here to showcase the solutions that are there, as well as to give prizes to the teams that have won. But thank you to all the hosts who have made sure that the competition this year is also a success. In terms of the numbers, overall, we had around 633 that enrolled in the various competitions and 265 submissions. These are unique submissions, but in terms of the total submissions, because some people submitted multiple times, we have over 3,800 total submissions. And these are from 65 countries and 26 African countries. And we have here the gender balance. We are roughly around 20% on the female. We still need to do better from the STEM perspective. And today, the prizes are in 3 categories. The first winner will receive a cash prize of 500 Swiss franc, whilst in this network traffic scenario prediction, they are going to receive $500 US. That's a slight difference. 500 for the first winner, 300 for the second or the runner-up, and 200 for the third. So in total, we are disbursing around roughly $3,000 US for the 3 or 3,000 Swiss franc for the 3 problem statements, but also we give out a certificate for the winners. And just a quick thank you to ULAC ZTE Fraunhofer for making this a reality. And of course, we also have a special issue announcement. All those people who submitted a solution, their reports, we would like to invite you to submit or to extend your reports into a paper, a journal paper that you can submit to our special issue. So thank you, everyone. And I would like to encourage you, to invite you to extend your reports as papers for this special issue. Now, today's finale session, we just finished the second part here. We are going into the participant presentations. So the format is quite easy. We have 8 minutes for each team to make their pitch, to make presentation of their solution, and we have 4 minutes for Q&A. And for each presentation, for each session will be preceded by an overview presentation from the host. So the host will have 3 minutes to present. And the sequence, network traffic scenario prediction, will be the first problem statement to be introduced and presented. Then we have the environment automotive QoS prediction, and then SDN security will be the last in the sequence of presentation. After we hear all the presentation, we are going to give awards to the top teams, and then we are closing the session. So good luck to everyone. Now I would like to invite Gaole from ZTE to give an overview of the network traffic scenario prediction. That was a problem statement hosted by ZTE on Zindi platform. So Gal, over to you.
Hello, everyone. Can you hear me?
Yes, please, you can go ahead.
Okay. I will introduce the background of this problem. Network traffic classification is important in many business scenarios. It can be used to accurately optimize network parameters or take different control measures based on the specific scenario. For example, in intelligent operation and maintenance, different fault types can be identified based on the traffic performance caused by each fault. In intelligent congestion control, rate control parameters can be configured based on the traffic performance to ensure high throughput, low delay, and no packet loss. During transmission process, is network traffic may be sent to the same port from multiple ports. As the output rate of the transmitting device is limited by the port bottleneck bandwidth, the input rate of traffic is higher than the output rate, resulting in the need for the transmitting device to allocate cache space to store burst traffic. This creates a cache queen at the egress port of the transmitting device. The queen length in the cache queen changes different based on different types of traffic. For example, queen collapse caused by different stream ratio and different roads are different. All these factors are different in variable service types, such as web search or distributed computing. As surface layer applications change, the traffic characteristic received by the same queen also changes, just like this picture. However, the state parameters of the traffic in different scenarios may not differ so significantly due to limitation in the collection device and context analysis is required to detect changes. Moreover, the number of the scenarios within a given duration is uncertain, and random switching between scenarios make it difficult to identify them. The the competitors should design a traffic scenario identification algorithm to determine the scenario that each time point belongs to, according to the state's parameters of continuous time obeyed from the port queen. The data set we provide to players include 78 pieces of training data and 19 pieces of test data. Each piece of training or test data is a log generated during one completely low flow sending process, and all data includes several similar processes. The training data includes the following columns, and the test data is similar. Time means the interval relative to the first flow sending time. Port PKT in means the input rate of the cache queen. Port PKT out means the output rate of the cache queen. Q size means the length of the cache queen. Label means the scenario type ID. The range is between 0 and 11. We use the calculated rate of the model as a scoring rule. That is the numbers of correct forecast time points divided by numbers of all time points. Thanks. Next, give us time to context. Okay, I'm finished.
Okay, thank you so much. Thank you so much for the presentation. Now we are going into the team's presentation. So each team has 8 minutes. I would like to first give the floor to Martin, who is going to be the first presenter.
Okay. Hello, can you hear me?
Yes, we can hear you.
Okay. Now the camera is working as well, right?
Yes.
Okay, perfect. Okay, let me share the screen. Okay, you can see it?
Yes, you can start.
Okay, perfect. So hello everyone, my name is Martin and I'm going to present my solution of the network traffic scenario prediction challenge that we just heard the introduction to. The outline, let's see if we can get through everything. I want to start with the problem statement, then I want to talk about the model network architecture as I used neural networks. I want to talk about the strongest hand engineered feature I found, how I compensated for short input length I used in my model, what I did in terms of ensembling and prediction smoothing, and then maybe we can look at the results as well. So the problem statement, as we just heard, we are given 3 time series of the input rate, output rate, and cache queue size of a network device. And we are asked to put out a time series that tells us which traffic scenario is present at each point in time. So basically, this is a segmentation task, as we're given a multidimensional time series as input, and we want to put out a time series as well as output. So because of this, I used one-dimensional UNets to solve this problem, because UNets are known to be good at segmentation tasks. And yeah, that's basically the reason. My model is shown on the right. I don't really want to talk about the specific parameters in detail because I don't think they're that new. I would rather like to focus on some other challenges I met on the way. 2 things I will mention though is that I used additional features, 6 of which were put in the model separately up here, and 1 of which I concatenated with the original input time series here, and which was then put into the model directly. Also, I used the input length of 2500, which is rather short because the time series themselves are over 100,000 time steps long. We will talk about this as well in one of the next slides. So let me talk about the hand-engineered feature I used, which I found to improve performance by quite a bit. It's the best feature I found. I called it the mode ratio. And it basically tries to capture how constant the input rate is. So we take the last 25 input values of the input rate for each point in time. We calculate the mode of these 25 values, and then we look at the ratio of values that are equal to this mode. So basically it counts how often the input rate goes back to the same value among these 25 input values. And what I found is that, for example, in this example, we can see that here in scenario 1, this mode ratio fluctuates quite a bit. So there are values between 0.2 and 0.6, but as soon as scenario 5 hits, the ratio goes to its minimum. And this is true for scenarios 4, 5, 6, and 7 on a large scale, as we can see in this box plot distribution of the mode ratio feature here, while the other scenarios actually show a more varied distribution. And this explains why this feature is actually pretty powerful when trying to classify the scenarios. The next thing I want to talk about is the compensating of short input length. As I said, I used input length 2500, which is rather short given the whole time series. And it leads to a problem, that is that on the edges of the prediction window of length 2500, the quality of prediction actually gets worse. So it's better in the center of the window. We can see this here. I defined a center portion of the prediction window by 2500 times R being smaller than 1. And we can see on the right how the accuracy changes when we change R. So when R is 1, so we use the whole window, or we evaluate the whole window of predictions, the accuracy is actually the worst. And it gets better, 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 and the maximum is actually at just using 1/4, like the center fourth of the prediction. So to overcome this problem, what I did is I actually created 4, like at inference, I created 4 predictions by sliding the prediction window across the input sequence, such that each time index I is predicted 4 times. One where the index is on the right part of the window, one where it's in these kind of in-between areas, one where it's in the center, and one where it's on the right, which gives us 4 predictions in total. I then summarized these 4 predictions in one multi-label logistic regression to put out the model prediction. And this sort of procedure actually helped with improving performance quite a lot. And it completely solves the problem of decreasing accuracy at the edges of the prediction window. Then let me shortly say that I used ensembling as well. The final submission is an ensemble of 4 of the unit models you saw before, and the assembling is done in the same way. We summarize the overlapping window prediction. So we take the 4 probability vectors of size 12 that we get out of the 4 individual models. We apply a logistic regression to them and put out one single probability vector of size 12, which is then the ensemble prediction. The last step, which might be interesting, is the smoothing I used. So once we get the probability vector, we can use the class with the highest probability as our prediction. But the prediction, if we do this, looks like this here in the first figure on the right, or at least my predictions look like this, where we see some fluctuating between classes. So to compensate this, I used the local majority vote to smooth the predictions. So basically, I was looking at for each time index, I looked at the 75 predictions before and after that time. And then I took just the majority vote on these 151 predictions and predicted this majority voted class, which not only smooths out the prediction, as we can see down here, but it actually increased the accuracy slightly. This is the visualization of the whole model. Just to summarize, the unit models create 4 predictions with these sliding windows that overlap to create left, right, center, and in-between predictions relative to their position to the prediction window. We summarize those in a logistic regression which gives us 4 model predictions. We summarize again in another logistic regression to create the ensemble prediction, and then we smooth that out with a local majority vote. The results are just like the details of the network you can find in the report, so I don't really want to talk about them in too much detail. However, the key points to take away are that the post-processing, the overlapping window prediction I presented, is basically essential to significantly increase the score. It also works better, which was interesting, than just taking some center portion of the prediction window. And ensembling and smoothing both increase the performance as well. And the best single performing model has 78.1% accuracy, and the final ensemble gets up to 79. Yeah, and then I just summarized some open questions which might be inspiration for the Q&A. But yeah, as I'm running out of time, thank you very much for your attention.
Thank you.
Okay.
Vishnu, maybe you can take over the Q&A.
Thank you very much. Yes, thank you, Martin. I don't see questions on here, but I have some questions.
Yes.
The hand engineered features, I think, I believe that is quite important point. I want to ask you about the spiky data. Let's say, I don't know whether you encountered spiky data in this data set, but let's say if you have spiky data, would still your averaging work or not? That's my question. So you have these spikes going up and down, and if you take the window, short window, you might still catch the spike, but whereas if you have a longer window, you may not catch the spike. That's my guess. So the question would be that would your solution still work in case of spiky data?
Let me ask you exactly what do you mean by spiky data? I'm sorry.
Yeah, so the inputs, the 3 inputs that you saw, they were having these graphs, right? So on those graphs, you could see the values going up and probably the plateaus at a high point.
Yes.
But it is possible that there are no plateaus, but there are spikes which goes up and down.
Okay. Yeah, I mean, I think it would still work. I don't see why not. I mean, one of the channels is bounded anyway, right? The output rate can't be higher than a certain point anyway. And I mean, but I don't see why it wouldn't work for spiky data. Do you have any reason why not?
Well, it depends upon the window size. I believe you have that. I believe you have some mechanism to do the window size as well. So yeah, I believe it should work. Can I ask Gao? Gao, do you have questions?
Oh, I have a question. That is why you construct the feature model radio, and can you explain the meaning of the feature, especially the model? What is the MK is?
Sorry.
Can you explain the meaning of the feature moderator and especially the model screens is?
This one? Yeah, here. Can you explain the MK is what is MK? MK is the mode of the last 25 input values of the input. So you look at a certain point in time, K, and you look at the input rate 24 steps before and between that, and you calculate the mode, so the value that you encounter the most.
What is the mode meaning?
Mode
what
is
is the meaning of the mode?
The mode is like if you have 25 values, then the mode is the value that you encounter the most. So if you have you have 5 times 1, and then everybody, all the other values are different, distinct from each other, then 1 is the mode.
Okay, thank you.
Okay, we are running out of time. We need to move to the next presentation. So I'd like to ask Shotunde to present. Martin, can you stop sharing the screen?
Yes, sorry. Okay.
Yeah, so Shotunde, can you share your screen and start the presentation? Yeah, please go ahead. Are you speaking? We cannot hear you. No, we cannot hear. Yes, I can see you, but I cannot hear you.
Hello? Can
Yes,
you hear me?
yes. Yeah, you can make full screen and start presentation. Can you start the presentation?
Can you hear me now?
Yes. No, not working.
A minute. Let me change to airport.
Okay, now I can hear you.
I'm not.
Yeah.
You can hear me, but I'm not using my earpiece now.
Okay. So can you present like that? Yeah.
Can I check to airport 1 minute?
Yeah, but we are running out of time. We have many presentations, so if you can do it quickly.
But you can hear me now.
Yes.
Okay. My name is Adeyinka Michael Shotunde. This is my presentation. I hope you can see my screen. Hello?
Yes, continue.
Okay. So network traffic scenario prediction challenge by two. Then the introduction part is the scenario classification is crucial task in optimizing network parameters and implementing management and control measures. The relationship between the traffic parameters and the associated scenario make this an important task to study. So what are some of the few challenges being faced by the traffic performance usually has startup parameters of traffic in different scenarios may not differ significantly due to limitation in the collection device. The number of scenarios within a given duration is uncertain, and random switching between scenarios can make it difficult to identify as well, among others. Then my proposed solution looks in this manner. The data set is a time series data set. Then going to my data preprocessing, which I see as each column representing an input channel, effectively creating a 1D signal. So from that to feature selection, selected features, which is all features selected, time, port, PK in, PK out, and queue size. Then to model selection. So AD 1D CNN unit architecture model was employed, where prediction was turned into 1D segmentation, then followed by model optimization. This is where I did my hyperparameters tuning. And these are the parameters used. From there to model training, then to my prediction and testing. The traffic scenario classification possesses a time series that are leading to the use of different types of available algorithms to be considered, be it machine learning or deep learning algorithms. However, the volume of the data provided creates a limitation for using ML algorithms due to the higher amount of computation power it will require, and also the level of domain knowledge in the implementing the required visual engineering techniques to tackle it if one must use machine learning. So consequently, the prediction task was seen as a 1D segmentation, whereby UNet was employed. So then my observation to this, the high number of time span by single categories during my exploratory data analysis inside the provided data set in the graphical illustration below, as you can see, it requires a particular algorithm that can keep this long-time memory. The graphical illustration further authenticates the huge amount of time it will require for processing the ML algorithm, which automatically demands for high computational power. So in that case, among all these stated algorithms that I intend to use, which is LSTM, GRU, which we all know that it can be used to tackle time series data, I decided to use one the convolutional neural network, CNN, at the end of, so seeing this thing as 1D segmentation. So my data processing, I didn't do much. All I did is just to use log transformation, yes, to each of the features. As we can see, the model architecture. So I just feel the architecture demonstrates fast training and the potential for achieving high score. The model takes advantage of the multiple input channels, treating the 78 examples as 78 different cases, akin to working with image. This network was built to include convolutional pooling and upsampling layers. These are all part of my model architecture. So the network used Twitter kernel size of 7, block depth of 1, and dropout of 0.08 in the encoding stage of the unit architecture to capture wide span of that label category. Then from there to my model optimization, where I have to do the combination tuning of all these parameters. We have layers, we have stripe, we have kernel size. So I only use just a single model, actually. Even though I'm still new to this particular, they won't give me edge in this
1 minute to finish.
Hello?
1 minute to finish.
Okay. So after doing all these parameters tuning, then here is my experimental result, which are divided into 4 stages: attempt 1, 2, 3 to 4. These are the hyperparameters. These are the public score. The last attempt 4, happens to be the best score. So then the discussion that I can say, the iterative improvements and adaptation made throughout the development process lead to the achievement of the competitive score. So though initially incorporating transformer-like attention layer did not yield the desired result, leading to a pivot towards a pure CNN unit architecture. So further improvement came from optimizing hyperparameters through cross-validation, etc. And an insightful observation during model output analysis led to the implementation of predictive aggregation code approach, which significantly not only improved the overall model performance, but also boost of generalized performance. Then the last conclusion, the network traffic scenario prediction presented the formidable signals segmentation task, closely resembling the segmentation of electrocardiogram signals. These happen to be my first algo competition on Cindy. So immediately I saw this particular challenge, I have to incorporate my idea into this. I think that is all I can say now. Thank you.
Okay.
Sorry,
thank you. I would like to give the floor first to Gaule and then to Vishnu for questions. So Gaul, if you have questions, you can ask.
I want to ask you, do you attempt the model SDN or GRU, and what's the accuracy rate of this kind of model? I want to ask you, do you attempt the model SDN or GRU? And if you have attempted, what's the accuracy rate of this kind of the models?
We cannot hear you, Adik.
I didn't end up using the GRU and LSTM simply because I did my comparison. After reading some papers, I could see that 1D units can save the long span memory of this data better than GRU and STM, because I could see that I can regard what's it called, the 1D unit as a better memory keeper, because all these time span memory have to be kept with the model for the model to perform better. So I didn't end up using either GRU or LSTM.
Vishnu, okay. You have a question?
Thank you.
No, I think it's okay. It's quite interesting that you have compared the ECG graph with this. That is actually a very good similarity comparison. But apart from that comment, I don't have questions. Thank
you. Okay, thank you so much. Right now, we are moving to the next problem statement because the third speaker is not here yet. So we'll check if he joins or not. At this point in time, I would like to move to the next problem statement on MAT environment automotive QoS prediction. I would like to ask Rodrigo if you have like some quick overview or some few words before we ask the teams to present.
Yeah, sure. I can give a few insights. So,
Adenka, can you stop sharing the screen?
I don't know, maybe I can try to share mine instead. Yeah, now.
Yeah, please go ahead, Rodrigo.
Yeah, sure. So I guess now you're seeing my desktop, and yes. I will now share the. So now you see the full screen with the presentation, right?
Yes, yes, yes.
Good. So yeah, as Thomas introduced the challenge, it's called multi-environment automotive QoS prediction, and it's going to be presented by me, Rodrigo Hernan Gomez, from the Fraunhofer Heinrich Hertz Institute in Berlin. But this is in fact a joint effort of many other partners, which I tried to list there, and they ought also to be mentioned: BMW, Ericsson, as well as the universities in Germany of Kaiserslautern and Dresden. And through Dresden University, we also got indirect support by Deutsche Telekom and Vodafone. So our goal with the data was to provide a benchmark to realize QoS prediction with the focus on automotive networks, because we believe that this is a very powerful tool to enhance radar resource management. So how we did this, we collected the data with the two said network operators and their LTE infrastructure in Berlin, and we did a number of drive tests in West Berlin, changing different parameters to measure latency as well as data rate in different conditions with several vehicles at the same time. And also while driving around, we designed the route in a way that it covers different kind of urban environments like these big avenues, broad avenues that the German's capital has, as well as more residential areas, an urban highway, and so on. And at the end, we provided the following capture data, where we have all the LTE stack, more prominently the physical layer parameters like SNR and RSSI and so on, also resource management parameters. Of course, the quality of service, we measured it both for data rate and delay, which constitutes the target of the data, and the position via GPS. Through the position, we also were able to gather a bunch of site information like traffic and weather. And we tried to label it as well as possible with all these different parameters, like measurement parameters, the operator, how we were driving, and this scenario. And the task we proposed to the participants of the challenge was to predict quality of service based on basically LTE information and position, and then to compare how it performs across the different environments, where environments can be defined as operator 1 versus operator 2. What happens if I train with operator 1 and test an operator 2? And this kind of questions. We also suggested to take a look into transfer learning and domain adaptation techniques for this. So I'm looking forward to watching what the contestants came up with. So, and with this, I'll finish my introduction. Thanks.
Thank you so much, Rodrigo. So right now, I would like to invite the first speaker, who is going to be Ndabuye. Please, Gideon, the floor is yours.
Oh, thank you. Is my audio correct?
Yes.
Is my audio coming through? Okay, let me share my screen. Hopefully it's can you see my screen?
You can proceed, yeah. You can proceed.
Okay, so my name is WS Gideon. I'm a fresh Bachelor of Science in Engineering, Software Engineering graduate. So I took upon this challenge, multi-environment automotive QoS prediction. At this point, I don't think this introduction is quite relevant in this case because I think the host has already provided some insight. So just a quick overview. The V2X is a communication technology enabling vehicles to communicate with other entities in the environment, so pedestrians, infrastructure, other networks, or other vehicles. So it aims to improve traffic efficiency, so autonomous driving, safety, but for all this to make sense, we need to make sure that the quality of the communication is reliable. So we can employ machine learning techniques to build quality of service prediction solutions so that we can be sure of the communication. So speaking of the data, this we were provided with the Berlin V2X dataset, which offers high resolution GPS location information, considering both cellular and siding radio access technologies, which was collected spanning 3 days by 4 cars. So I used the data set, but it was already sampled to 1 second, combining all the sources. So we have a lot of information, physical layer parameters, cellular the resource, GPS, and other side information like traffic and weather. So upon beginning the challenge, I had to define my specific objective into this challenge because the data had a lot of information. So I had to select a perfect feature that tells me about the quality of service, which was the downlink data rate. And also, as we have seen from the first presentation, Mr. Rodrigo, they were 2 operators from the data set. So I had to select operator 1 to be the train and operator 2 to be the test so as to kind of maximize the generalization capability. Okay, so this violin plot on the right side shows the distribution of the downlink and uplink data rates, which tells us the distribution. So you can see that the downlink has more data than uplink, and you can see that the distribution kind of spans a larger amount compared to the uplink. So this is why I selected the downlink data rate as my target QoS feature. So here's the final objective I came up with: to build a QoS prediction model using minimum features possible that would make sense, using the operator 1 set and evaluate on the operator 2 set to achieve the high R² score. So the biggest part of this was the pipeline that I created. I just created 3 functions and put them into a pipeline. So the first one, actually, what it did is getting the desired data based on my objective, which is taking only the downlink data rate, removing any other rows that have null data rate values. And then the second one, remove columns that I think that have no experimental effect, and the ones that won't help us much because we saw a lot of missing values when, for instance, coming to the fact that it was sampled to 1 second and some data was collected on a span of 5 minutes, seconds. So we had a lot of missing values. So I removed every column that has more than 80% of missing values. This is what the second column did. I mean, the second function of the pipeline did. Then the final created new features from the time. This is the hour. And then I fill the rest of the missing values to a 0, then remove some other unwanted features. So we can see that the input data that was given was around 200,000 rows. So through the pipeline, we just get a little over 25%. There's 50,000 columns. Yeah. So to go to the feature selection part, because we still have 106 features. So I guess the feature selection part, we needed to build a model so that we can get the features that contribute more to the target QoS feature. So I did a quick LGBM regressor model, plug and play default features, which gave me an R2 score of 91%, which was kind of surprising. I was expecting lower. So, but this was 106 features. This is too much for the objective that I set earlier. So then I came and removed some more features. As you can see on the left side here, device, longitude, and latitude. As longitude and latitude wouldn't be so useful here because, and thinking of deploying it to a larger scale, then the Berlin part, well, wouldn't be so useful to use the position features. Yeah, so that's what I saw and didn't have experimental effect either. So after plotting the feature selection from the model I trained up here, I did this line graph and sorted them from the highest to the lowest. So I used this trick that says when you plot a line graph, it's more like an elbow technique that's used in clustering. But here it was like looking at the features at the point where we have features having just a very gentle slope, where the differences in features in values are kind of not so much. So you can either take all of them or remove all of them. So I selected 50 to be the threshold as the value of feature importance. So any feature that is lower than 50 was removed. So doing that, I just remained with a total of 9 features. So this is a quick overview of how I went from 91 R2 score to 94. This is the initial one we saw with 106 features. Then taking the 9 features that are obtained after putting the 50 threshold, we get 93.66. So it makes sense that we had a lot of noise from the features. Then after tuning the model and using K-fold a training so that we can have like retrain and that technique. So I ended up with 94.2% of the R2 score. So this is the visualization that shows the default and the tuned LGBM, both on 9 features. Then after that, we have to see how well the model that we've just trained gives using the regression analysis part. So we can see here the feature. Okay, thank you. So we can see here we have these are the 9 features. So it makes sense that we only have downlink, things like speed. So these all made sense why that they gave a better performance than the 106. So we can see the plot is not the best, but we can see that it's only very small points that are way off the regression line. So that was that. So a discussion is more on the how we can get to best the performance. So the GPS information wasn't useful. So if we have the data that spans in in a bigger geographical area, then we can maybe use them. This is how we can see the plot of where the cars kind of rotated. So it's kind of it's not a big geographical area to actually consider it for a large deployment. So also we can also think of time. So if the data is recorded for a longer time, we can also have things like weekends, weekdays, the work hours, and stuff like that, which weren't that informative in this one. also the missing values. So conclusively, we had just 9 features. Gave us 94.02 of the IATU score.
Let's finish. We are running out of time. So,
yeah, so
okay,
for
Q&A, let me ask first Rodrigo and then Vishnu to ask questions. Rodrigo.
Yeah, thank you very much for the nice presentation, Abuya. So I'm glad that you showed this list with the selected features that you came up with. Because I mean, you did a very good report, but it wasn't that. I mean, I think here it's much clearer. So, did you? I mean, did you reflect on this list yourself, like whether it makes sense or whether it's realistic or so? Like, I mean, it's of course you have full right to use so-called active program parameters for this, like the ping and jitter, because we didn't restrict this in the first place. But I mean, I wonder. I really like your approach. I think it's the right approach. This feature selection and so on. But I think we could. I mean, it's something we need to reflect on. So I don't know. Like, do you have any further comments on this final feature list?
So yeah. Let me say something about. Okay, so initially I had to do some research on what exactly intuitively should have an effect towards this. Mm-hmm. So I was doing in a two-way manner. So intuitively and research, then mathematically, like experimental. So yeah, in the end, it's like 1 or 2 features which were intuitively before, like they made sense, but it's like 90% of, let me say 95. It's because it's 11 out of 9, so it's good. It's coming 90-something% of features were, through research, made sense to be the only one that should give us a good score. So it was two-way, intuitively and experimental. That's
okay. Okay, thank you very much.
Yeah, thank you very much. Yeah, I think in fact, I was very curious to look at your list as well. This is very interesting list actually. I actually the side informations which were there as part of data, most of them don't make here. So it's very interesting that most of them don't make here. Yeah, I wonder why none of them matters. Maybe the speed. I see you have picked up speed. That's not a side information, but I believe that's here. That's the only one which is non-radio data. I mean, let's forget ping and jitter. But apart from that, the non-radio ones I can see speed. What do you mobility pattern? So let's just generalize speed into mobility pattern, right? So if I look at side, I can get some mobility pattern. Does that help at all to analyze that direction at all? Do you think that makes sense?
Yeah, there are things like mobility, you mean? Yeah, it should because I think that's where you get things like interaction between other objects, like line of sight and stuff like that. So I mean, it should. So one thing I should also point, I didn't mention, is on building this particular solution, I was also considering in a large scale deployment. So things like weather, or which was specific to Berlin, I kind of weren't so confident in using them because at a larger scale, the model kind of gets biased that, okay, we must have weather of this kind or just this kind, but at a larger scale, I don't think that's true. So I stuck with the things that would be true in any environment, most. mostly.
Okay, yeah, great. Yeah, thank you very much. Yeah.
Okay, thank you so much. I would like to move to the next presenter. So the next presenter is Dhruv Kapoor. And can you share your screen, please? Yes, and go ahead with the presentation.
Good morning. Yeah. So the objective function that we had to solve was to find a machine learning process to accurately predict downlink or uplink. And our machine learning process would be evaluated on the amount of features we used, the R-squared value, as well as the generated report. And there was a little caveat where we had to split the data set with the target and source domain. So the way that I decided to approach this problem was first we look at feature selection. So we wanted to choose the variables that we know affect data rate. Then we want to choose the domain on which to split the data. And then we can start to analyze and evaluate our algorithm that we created. And for this specific problem, we found that using an artificial neural network seemed to be best. So the way we split the data into, it was P-cell and S-cell and the miscellaneous data sets. So variables led by P-cell, such as P-cell, RSRP, RSRQ, SNR, max. Same with S-cell. So we got primary data results and secondary data results. And then all other variables that we said did not fall under P-cell and S-cell, we grouped under miscellaneous. So things such as ping or GPS data. So in the beginning of our feature selection, we decided to select from the known. So we wanted to choose features that we know affect downlink. So variables such as signal quality or downlink transfer rate. And then after we tested the ones that we knew affected downlink, we wanted to use trial and error on the unknown variables that might not necessarily affect downlink data rate speeds, but if we found in our artificial neural network that it improved our neural network, we would include it in our algorithm. So this is an example feature selection that we ran. So as you can see in the first one, we started with our P-cell, RSRP, RSRQ, RSSI, SNR. So these are some variables that we know affect downlink data rate. Then we increased the amount of variables that we're using in order to help improve the neural network. So you can see that we have a variety of different criteria that we evaluate our algorithm on. So we have R-squared, we also have mean absolute percentage error, among other things. So then we increase the amount of features selected in P-cell and S-cell, and we go on to evaluate our algorithm after that. So yeah, so our feature selection, so once we finished with that, we looked at unrelated features, we looked at different models, different train and test sizes, and as well, we employed a strategy-specific selection on the amount of features we use. So we add or remove features that we didn't see any results or negative results. So we also had different domains that we could use for our train and test sets. So some example domains were park and avenue, which was data collected around parks, is used to predict the downlink that we have around avenues. We also have operator 1, operator 2, data collected by different operators. We could use the uplink data to try and predict the downlink. Or another example would be data collected on highways, which is used to predict the data that we would collect in residential areas. So finalizing the algorithm was, we decided that splitting the train and test sets based on the park and avenue were the best for our algorithm. And this is possibly due to the similar levels of interference. For example, the similar amount of buildings or open space or greenery around where we would be collecting data. Additionally, we would like to evaluate our R squared. So when we switched from a randomized training test set, our R squared value decreased. And that might be due to the fact that we were using different sizes. So our training test set were a little bit closer together in size. And to, I guess, push this algorithm onwards in the future, we could add more features to our algorithm, or we could continue to train the data set a lot longer than we did in this scenario, or we could change domains and view the results after you change domains. Thank you.
Okay, thank you. That was quick and nice. Okay. Now I would like to start the Q&A. I will ask Rodrigo and then Vishnu to ask questions to you. Rodrigo, the floor is yours.
Yeah, sure. Thank you. Oh, sorry. Thank you for the very concise presentation. I would like to go back to your last slide about exactly the. Okay, so I mean it's a very reasonable approach to just like try out these different let's say possibilities for domains and then going for the one that works the best. This part and your. I mean, your thoughts are completely right. Like Park and Avenue, they are. I mean, they're very similar in the sense that in both of them you have like these very broad roads, and you will have for the most part line of sight with the base stations. I didn't quite fully understand the point you made about the evaluating R2. So you said you tried the same algorithm, but you did a random train test split. Did I understand this correctly?
Yeah. So before we decided on the domain, we were looking at a normal 80-20 train test split of our data. So we would split the data 80% for our training set, 20% for our test set. So that was a random selection. So when we moved over to splitting the data based on domains, we were looking at, and then this was in domain selection, we were looking at the percentages that each domain showed up. So we were looking for one of the closest match percentage-wise of the data set that we could match up to as close to as an 80-20 train test split as possible, so that we could have a similar algorithm than the one we just created. So after we found that random one, an algorithm that worked for the random train test split, we decided to move on to the domain train test split.
Okay, and so then for this random split, you put together the data from Park and Avenue, shuffle it, and then split as 80-20.
Yeah, exactly.
Okay, and did you think also about the maybe some argument based on correlation, like when you shuffle the data, then do you think this also affects the correlation between train and test data samples, and thus the, let's say, this like independency between train and test domains may be flawed?
The thought process behind the train and test data was that if we randomize it, we allow for the algorithm to be able to, I guess, change itself for a variety of different situations.
Mm-hmm.
So by doing that, we could create a general model that we know works for a certain amount of features and certain features. and then we could, I guess, extend that general model to the more the specific domain that we had for this challenge.
Okay, interesting. So thank you for your answer.
Yeah, thank you very much, Drew. There's a very nice presentation. I have feature selection slide. In your feature selection slide, 2 questions. No, the next one. So the 2 questions, you seems to have selected pretty much already related things. Forgetting the ping for now. How did you correlate? Do you already know that which one correlates correctly from your reading of the domain, or did you refer something? As my first question. Secondly, there is no side information used at all. I mean, you see, there are some side informations which are part of this data set which are completely not here. That's quite interesting. What is your viewpoint on that? Can you please explain?
Yeah, of course. So for the feature selection, we had some ideas on what would affect downlink data rate. So there are some variables that are known to be that if you change them, it will change the downlink data rate, and some of them have to do with signal quality. So that's why we started with RSRP, RSR, QoS, and R, because those are all measures of signal quality. So then after we had a couple of signal quality, we decided to expand our scope on different like miscellaneous variables, like I said, but the beginning was based in the reading and understanding of 5G networks and the signal quality. And in terms of the secondary data sets that you mentioned, unfortunately, there wasn't enough time to examine those more closely.
Interesting. Yeah. If I can ask one more question, the split between train and test, did you consider the secondary information when you split the train and test?
In terms of the secondary data sets or different? No, I did not.
Features. I mean to say the other features.
Oh yeah, so we were splitting the data randomly with other features. So we were testing, for example, we were using feature selection to test if, let's say, we were trying to add altitude. We would also have that in our train and test data split.
Okay.
Thank you so much. We are running out of time. I would like to request the next presenter, Kishin Zhang, to make the presentation.
Yeah, sure. Let me share my screen. Can you see my screen now?
Yes, please go ahead.
Yeah, sure. Hi, everyone. I'm Qixin Zhang, a team member of UIM 5G. I'm a second-year computer science PhD student from University of Minnesota, advised by Professor Zhili Zhang. My research interests are security issues in networking and generative AI for differential video delivery in 5G. Here are my team members, Wei Yi and Steven Slater. First, let's recall the challenge. Berlin V2X dataset provides extensive wireless measurements from Berlin. Our research challenge is that can we effectively train a model on cellular communication data from one operator and adapt it to accurately predict the data rate on another operator's data? Now you might be wondering, why should we even care about this challenge? Every day, more vehicles are becoming interconnected, creating a massive web of communication. And we want to ensure that data transmission between vehicles and infrastructure is consistent and dependable. However, a significant challenge arises when the data set itself comes from varied distributions. Our primary data resource is the Berlin V2X dataset offering cellular network matrix. And from Figure 2 in Berlin V2X paper, we can see the similar downlink data rate distributions between the two operators like in avenue and residential, while there are different distributions in park and heavy. So how do we tackle this? The solution lies in domain adaptation. Domain adaptation is about taking what a model has learned in one domain and making it applicable to another. It's crucial because in the real world, data is messy and diverse. Our model needs to be versatile. Here is our proposed solution to solve this challenge. First, we set different operators as source and target domains, and do the data exploration and pre-processing to ensure that our data is in the right format and quality for modeling. In this approach, our novelty is to use the combination of the models that have different functions. For feature selection, we choose to use random forest regressor for the feature selection, because not all the features are equally informative. Using this method allows us to identify the most significant predictors for our continuous target variable. It also aids in reducing overfitting and computational cost. Random forest is a collection of decision trees that aggregate their predictions to provide a more accurate estimate of the continuous target variable. As shown in the table, we can see the features that most significantly influence the downlink data rate. With our features ready, we harness the power of the domain adversary neural network. The DAN model is a multi-task learner. It consists of 3 components: the feature extractor, the main task regression, and the domain classifier. The feature extractor takes in the data and transforms it into a format that's easier for the model to understand, and the main task regressor tries to predict the data rate. And the domain classifier tries to distinguish if the data comes from the source or the target domain. Enter the gradient reversal layer. During the training, this layer essentially reverses the gradients for the domain classifier. The goal of this layer is to help the model to learn features that are useful for the main task while being invariant to domain shifts. So the domain classifier gets confused, ensuring our features remain domain agnostic. However, in our task, it's essential to know that while both domains data were fed into the model, the primary data rate regression task was trained only using the source domain's data, while the domain classification task used the domain's labels. Now let's see the results. In the result table, the DAN model's performance is tracked across multiple epochs. Notably, by the final step, the loss has refined to about 0.1. Additionally, we used R2 score to evaluate the model, which quantifies how effectively our model can predict data rate in the target domain based on its training in the source domain. And we achieved a good score of about 0.8, which suggests the model's capability across different distributions. And in conclusion, our efforts in this research illuminate the effectiveness of the combination of the 2 algorithms and the promise of DAN in bridging data distribution discrepancies. Our model managed to attain an impressive R2 score on the target domain. This signifies that although there are differences in data distribution between the 2 operators, our model effectively generalized and made reliable predictions. Thank you for your time and attention. Let's dive into your questions.
Thank you so much. I would like to ask Rodrigo and then Vishnu for Q&A. Thank you.
Yeah, sure. So thank you, Grijin, for the presentation. I have to admit, while we were preparing the challenge, we had domain adaptation in mind. So I'm very glad you actually used it, and from the finalists, you were the only one to do so. So the obvious question that comes to my mind is whether you compared the results with and without domain adaptation. I mean, you could have as well just trained on the source domain and tested on the target domain without any domain adaptation strategy. So did you compare? Did you do this comparison exercise?
Yeah, sure. Yes, of course. We compared two situations. In the situation without the domain adaptation, we also achieved a good R2 score, but the variance is extremely large. Like the loss could be like trillions or billions. So it means that the prediction is still invalid for us to use. So with the DAN model, we both achieve good R2 score and the loss values. That's why we chose to use DAN model here.
Okay, so the main benefit of domain adaptation or of this domain adaptation technique is to reduce the variance of the result, if I understood it correctly.
Sorry, I didn't hear. Could you repeat?
So, yeah, sure. So if I understood you correctly, the main benefit of domain adaptation here is to reduce the variance of the result.
Yes, and it also avoid overfitting.
Overfitting. Okay.
Yeah.
Thank you. Thank you very much.
Yeah, sure. Thank you.
Thank you very much. Yeah, I also think that the approach of domain adaptation which you used is quite interesting. Can you tell what is the what kind of target domains did you use? Could you please explain again what kind of target domains did you use?
Do you mean how do I like split the data into two domains?
Yeah.
I just set one operator to be the source domain and another to be the target domain. It depends on the operators.
Okay. Yeah. In that case, does the side information matter at all? Because the each operator there is a split, yes, but there is also location and side information which is going along with that collected data, right? So
yes,
each domain has side information also along with it, which may be affecting your performance, or what do you think?
Yeah, the locations might be a very important factor. Maybe next time we will try to like set different scenarios to be source domain or target domain, but this time we just set different operators to be the two domains.
Yeah, I think you're right. Maybe to look at first in a location basis and then look at this split that you have done is quite interesting approach. Yeah, thank you.
Yeah, thank you.
Okay, thank you so much for the presentation. Right now, we will go back to the first presentation on network traffic scenario prediction. We had last presenter, Alabi, who is joining us. I will share the screen from my side. So, yes, Alabi, the floor is yours. You can just tell me next once you finish. I cannot hear you. Can you try to speak?
I'm Alabi, and I'm presently working on my PhD graduating in this coming month. And today I will be presenting my approach to solving the network traffic scenario prediction. For this particular challenge, I focus on using 1D convolutional neural networks. And as events unfold, you get to know why I take this decision and how this decision was actually a good one for the particular task at hand. Next, please. As an outline to what I'm going to discuss, basically, I will start with an introduction of this challenge in terms of what and why the challenge is related to why and to the particular approach using for this. And also, I'll try to give an idea of the challenge that can be faced by using machine learning algorithm or approach for this particular kind of data, and also why deep learning can actually be the main way of solving the problem without wondering or getting overwhelmed with challenges of machine learning. And from there, I'll move on to the key advantage of the approach that I use and the novelty that comes with it. And finally, I'll be having a slide on the results as well as a conclusive details of the approach. Next, please. As an introduction, network scenario, as we know it, actually helps in a proper resource planning. Because if we know exactly what our network is going to be used for and the kind of traffic that is going to come with the network usage, then we are going to plan well. And for this reason, I see that the challenge or the particular task is something that's really worth investing time and resources into. Also, besides this reason for the particular task, the data itself needs to be looked into. When we want to solve a particular problem in artificial intelligence, the first thing we actually have to work on is a little form of EDA, basically to explore the data and try to understand the kind of data that we have to work with and try to understand how we are going to work with it. So looking at this, I found out that a data itself is time series. Basically, it needs time series approach to be able to solve it, because the data, in fact, even the data have a particular column on the time stamp, though the time stamp is in microseconds, which is not really an issue for us. It's just to show that it's in time series. And the other thing that matters for this is that while the data might look to many people to be a kind of machine learning data, because of the lightweight nature of the data is quite small in terms of the number of instances that we have to work with. Something that is very peculiar with it is that the data has some properties that makes it challenging for machine learning approach, which we are going to see as we move on with the presentation. And beside this notable observation when it comes to machine learning, being the time series data, we have seen a lot of approach that can be used in deep learning for time series data. And also time series and also deep learning has been used for some tabular data in literature, which led to my decision of using something that relates to that. Next, please. The challenge. The challenge that I'm trying to mention here is regarding to the challenge of the data. And the basic thing that comes with the data is that the target value for this particular data is not completely random. I meant that it's not completely random in the sense that it has a time, it's like multiple timestamp or multiple steps do have the same prediction score. Like, let me say that they do have the same class. And this kind of thing can be best looked at as a kind of a segmentation. And for us to work with segmentation, and we have already laid down algorithm that is already applicable to segmentation in deep learning. Although most of these algorithms are used for 2D data and 3D data when it comes to volume segmentation. But in this particular data, it's 1D, so we have to look for the best way to handle these things. Another thing that is being challenging here when it comes to using machine learning for it is that the huge number of rows, data is presented in microseconds. And if we have a data for just 3 seconds, we are going to have a data that spans like 3 million data just for 3 seconds. If you are dealing with microseconds time frames, this kind of huge number of rows normally led to some computational restrictions when it comes to machine learning, because it's more like you are trying to get a single row predicted by that same row. So it's like you're going to process the whole millions of rows, and this thing can have a serious impact on your resources when you try to use a machine learning for it. Next, please. Next slide. Oh, thank you. Because of these aforementioned challenges of machine learning, I tend to look into the best ways to handle this with a deep learning approach. And some of those things that can be used for time series data like this are actually LSTM and GRU, because this algorithm has been structured to work with recurrence. And when we say recurrent, it means that trying to predict the next time from the previous prediction and some input of the present time. And this is exactly what is logical to do when we have something, when we have the target spanning multiple instances or multiple time steps, then the model can benefit a lot from the previous prediction. Of course, when we want to use machine learning for this, we can try to do some kind of delay and the likes. But as I said earlier, there will be problem of computational resources because we have this data presented in microseconds, and just 1 minute of data is going to be like 60 million lines of data if you want to look at it in terms of micro presentation. But long short-term memory as well as gated recurrence unit has been tested and has been tested for time series data, and they can be useful. Although for this particular scenario, they still have their own problem as well, which is the fact that they are time intensive, because you are trying to predict something.
1 minute to finish. You have 1 minute to finish your presentation.
Okay, so they are time intensive, and because of that, we can consider something else, and which is why I move on to using a 1D CNN, which is simple to deal with. Prediction is turned to 1D segmentation, and we basically modify a unit to 1D. Next slide, please. The key advantage of this approach is basically the fact that it's completely eradicate feature engineering that we need in machine learning. There is no need for any kind of complex preprocessing, and it reduces the computational power requirement. Next slide. And using unit 1D segmentation approach, I basically tweak the units in several ways. One of those things is that I try to expand the scale factor to 5 from the regular 2 that is used in images, because we have a big length of data. We try to aggregate so much information as we go from one step to another. And also, I use a squeeze and excitation block to encourage some kind of attention between the layers. As we can see from this slide, you can see that the result varies based on the changes in the filters, and there are some areas for improvement in case we try to move on with this kind of approach for some other data. Thank you so much for your time, and all questions are welcome.
Okay, thank you so much. I would like to ask Gao for questions and Vishnu. So Gao, if you have some questions, please.
I have a question. How do you choose the parameters of the model? For example, the kernel size, just for fitting.
Thank you. Parameters chosen is just in terms of overfitting of the model. Basically, since looking at this particular slide, you can see that I put some key features there, like the scale factor, kernel size, and block depth. These are important parameters to be considered. First, the scale factor. We have a data that spans like a millions of information just for a particular scenario. But if I try to scale it down by 2 by 2 and the likes, I might need to go so much in depth for me to get a reasonable data, a reasonable feature length from this particular network. Because of this, we try to squish in more of this thing by trying to limit, by trying to aggregate more information. And besides this thing as well, since we look at the target data, the target output, it spans like a particular target value spans so many instances. We can have the same class predicted for like 20 or 30 instances. Because of this as well, it looks like it means that the kernel size that I'm going to use should be a bit broader. And that is why I try to move away from the regular kernel size of 3 to 5 as well. Of course, to make it even more promising, we can actually play with this kernel sizing as well. And several other features are being changed based on the theory of understanding of how the data looks. And the only thing that we try to limit here is that as we increase the feature sizes, of course, the parameter size is going to increase, but to make it more manageable, we try to increase the dropout rate so that we don't just overfeed the data, overfeed the model for nothing, to make it more generalizable to unseen data. Thank you.
Yeah, thank you very much.
Thank you for your answer.
Yeah, thank you very much. Interesting, very interesting results. Thank you. You mentioned about maybe augmentation and maybe tuning. I want to ask about parameter tuning and augmentation. What are your thoughts? What is possible?
Yes, thank you. Starting with the augmentation. Most of my models, all my models basically was not trained with very serious augmentation. I basically focus on avoiding overfitting by using dropout in the last layer of my model, so that I don't just fit all the data on the model and it fails to predict unseen data. However, there are so many things that can be done in this approach. I first tried to do this augmentation, but I later stopped when I noticed that I need so much time on this and I was busy with so many other things. One augmentation that can be considered is flipping, because we have the data to be sequentially being presented. We have the data, the time is increasing. We can decide to even change the timing orders. Like if we can change the timing order, this is one thing that can be done. And one other thing that is normally used in this kind of scenario is introduction of noise. If we try to introduce some noise into the data, this can also help the model to learn more of irregularities that can happen in a real life, because this data actually, they are real life scenarios. Irregularities are very common to these things, and noise can be used to model this kind of irregularities. But for us to push noise, we have to be careful of the kind of noise we are going to put. Of course, it has to be white noise, and it has to be quite minimal in terms of the SNR of the noise compared to the real data as well. This thing requires some time to go into it, and of course, this time will be profitable at the end because it's going to make the model more robust to data of any form. In terms of a multi-batch training that I mentioned as an area of improvement, most of my basically all my data, all my models was trained with a single batch size of 1. We noticed that the data that is given to us actually have a varied number of time steps. Some of the networks that is given to a network instance that's given to us might be a recording of 6 minutes, for example. The other one will be of 10 minutes. So trying to train with multiple of these things at once might be a bit challenging, except I try to crop the data to make them to be on the same side, because to fit the data together for training and when it comes to deep learning. However, this is going to be promising in the sense that the model will understand domain generalization, because we are going to have a very kind of property of one network to the other. But if you are training with multiple batch at once, like 2 or 3 or even 8 kind of different network, the model will understand this thing easily compared to when I'm training with a single batch. Like
I have to cut you there. We are running out of time. So let me push to the next presentations. We are going into the intrusion and vulnerability detection in software-defined networks. I would like to ask everyone to give a very brief overview. We are running out of time, so everyone quickly, and then we go into the presentations.
Okay, Thomas. As mentioned before, SDN security is one of our main focus area. So we have various SDN products as ULAC communication, and the use case, which is SDN security, is very popular research area. When we look at today's networks, one of the most significant challenges we observe is the anomalies in the data patterns. So this is the typical feature of a live network data. Therefore, beyond being a fundamental AI/ML design challenge, another critical aspect of this challenge is utilizing the most efficient pre-processing operations for the data set. So we have evaluated our solutions, or we have some evaluation criteria for our use case. These are data pre-processing, model design and architecture, and performance results, and also reporting. So I will just give the floor to the participants because we do not have more time. Thank you, Thomas.
Thank you so much. I would like to go into the first team. Sotiris, to make the presentation for the first team to present. Anyone joining on neural network, yep. I would like to ask you to refresh your browser so that you can keep continuing to see the session. Send it a few minutes.
Okay, let's go. Hello, everyone. My name is Sotiris Hadjimiltis, and this is our proposed approach to create an intrusion vulnerability detection system for software-defined networks. Now, in this project, we aim to create a machine learning intrusion detection system that will distinguish between normal and malicious data traffic. Now, normal data traffic makes up most of the data traffic, whereas malicious data just occupies a small percentage. Having a quick glance at the table, we can see the high number of benign instances and the low number of individual attacks. Not having equal data distribution for each data traffic can pose a big problem on the final intrusion detection system performance. And our aim was to develop a solution capable to handle the class imbalance problem while achieving a strong classification performance. The outline of our approach is illustrated in the slide and comprises of 4 major stages. Those are data preprocessing, feature selection, data resampling, and then classification. Getting a view of the preprocessing stage, we have 4 minor tasks to apply to the initial datasets. First, records containing none or infinite values, as well as duplicate records, were dropped. Then features containing -1 values were replaced with the mean value of the respective training feature. Subsequently, 8 zero-value features were removed. And finally, the label column was encoded to transform the categorical values into numerical ones. Now, for feature selection, we used random forest classifier feature importance. And what we did was split the trained dataset in 5 faults, train a classifier for each fault, compute the average importance of every feature over the 5 classifiers, sort the average importances in descending order, and keep the top n features until we reach a cumulative importance of 90%. In our case, the number of features were 34. And on the figure on the right, we can see our approach feature importances along the cumulative line. Now, let's talk about the most important stage of our approach. There is an extensive literature that provides ways to handle class imbalancing in dataset. Some approaches include random undersampling that randomly removes instances of the majority class, random oversampling that just adds copies of existing instances of the minority classes, and cost-sensitive training, where learning algorithms are getting penalized more when they misclassify minority classes. In our approach, we combine 2 of the most effective resampling techniques, which are SMOTE and TOMEX-LINK. Applying either one technique can show improvement in the results, but combining them together can make the difference. First, we use SMOTE oversampling technique to create a better class distribution in the dataset. SMOTE works by picking an instance of the minority class, compute its k-nearest neighbor, and create an instance that lies between the instance and the neighbors. TOMEX-LINK now, as shown in the figure, TOMEX-LINKs are close in distance pair of instances that belong to separate classes. we remove the instances that belong to the majority class in order to increase the space between the two classes that may facilitate the classification performance. Now, concerning the machine learning models used for this project, we decided to mostly use tree-based algorithms since they have an extensive use in the deployment of intrusion detection systems, are easy to implement, fast to train, and can provide interpretability if needed. Our chosen models include k-nearest neighbors, decision trees, bagging classifiers such as random forest, and XGBoost. Some of the models were used as benchmarks. Moving on to our results, training of the models was performed using 4 variations of the initial dataset provided to evaluate the performance fluctuation. Those datasets are the original dataset, a feature-reduced dataset, a resampled dataset, and a feature-reduced and resampled dataset. This table shows the test results obtained by applying different combinations of classifiers and datasets. The best overall performance was obtained when XGBoost was trained with a feature-reduced and resampled dataset, achieving an accuracy of 99.9% and an F1 score of 99.96. And furthermore, the best per-class performance was achieved when the decision tree classifier was trained with a feature-reduced and resampled dataset. Now, getting a more detailed look on the results of the XGBoost, we can see from the confusion matrix that the XGBoost classifier performs good detecting benign instances. However, it lacks performance on some minority attacks. Those attacks are minority classes that have insufficient training instances, leading in a difficulty to train the classifier to detect them. If we now observe the performance of the decision tree model trained with a feature-reduced and resampled dataset, we can see that the performance for the minority classes increased in most of the cases. Let's do a side-by-side comparison of those two models to have a clearer view. XGBoost indeed shows a better performance identifying benign data, but if we compare the minority classes, we can see that the decision tree with trained on resampled data made some improvements. A final ablation study was made to evaluate the effect of the resampling in the performance. On the left, we have the decision tree trained with a feature-reduced dataset, and on the right, we have the confusion matrix of the decision tree trained on a feature-reduced and resampled dataset. Having those confusion matrices, we can indeed validate that resampling can improve the performance of the minority classes. To conclude this presentation now, our best model achieved an overall accuracy of 99.9% and an F1 score of 99.96. The best per class performance was achieved with a decision tree model trained on a reduced and resampled dataset, and the training times were roughly 29 and 8 CPU minutes respectively. Finally, some takeaway points. Reducing the number of features doesn't always lead into a worse performing model if the features are descriptive enough. Secondly, data resampling can most of the times help boosting the performance of minority classes. And thirdly, depending on the task to be carried out, the appropriate machine learning model must be chosen. Finally, we believe that the conjunction of those 3 components is what can really improve the performance of the intrusion detection system, and not just, let's say, a more sophisticated classifier. Thank you very much.
Okay, thank you so much for being on time. I would like to ask Evren to ask questions and Vishnu as well. Evren, the floor is yours.
Okay, hello, Sotiris. Thanks for this nice work. You mentioned a little bit, but in the future direction of your section of your study, you mentioned the possibility of application of different data imbalance handling methods.
Yes.
So, in your current work, you choose some techniques,
yes.
But regarding your anticipations, what are the other methods that can provide the advantages regarding your current solution?
What are other methods that can be applied instead of, let's say, resampling?
Yes, exactly. And one more question.
Yes.
Does deploying more complex methods to handle the imbalance in the dataset mean increasing the complexity? Does it create any disadvantage for any manufacturer? I mean, the hardware design perspective, because we are deploying some SDN products And when it is time to deploy some machine learning algorithms from data preprocessing to prediction part, does it increase the complexity? Just your idea about it.
Okay, firstly, let's say other alternative solutions instead of resampling can be we have hierarchical classification. If we have an imbalanced dataset, we can start by classifying, let's say, benign and attacks as a binary classification, and then continue by splitting our attacks that have less and less instances into more into more deeper levels that can classify more specific attacks. That's one alternative. And about the complexity that can be introduced when using, let's say, oversampling, resampling in general, I don't think it makes the model much more complex. We just need some time in order to create or remove the data, but the model's complexity, in my opinion, doesn't increase. I don't know if is that enough?
Yeah, clear for me. Thank you, Sotiri.
Okay, yeah, you're welcome.
Vishnu?
Thank you very much. Yes, I think this is a very comprehensive presentation. Thank you very much.
Thank you.
I want to ask, I really like your last slide. It's actually, you explained that the flow diagram quite well in the last, that one. Yeah. So I want to ask you, let's say you had to design the data set maybe next year.
Okay.
What would you tell everyone to do? What would you suggest everyone to do? What are the how can we augment the data set, please?
Okay, I think to start with, the data set was like a really good data set because it made the participant to have a look at it. It wasn't like ready to be used. You had duplicate records, like corrupted records inside, which is something good. But the only thing that it may improve a bit, make the competition a bit easier, is just put a bit more put some more instances of like minority classes inside. Yeah, that's it. Like, apart from that, yeah, the dataset was pretty good to work with.
What about the baseline results? So everyone in his presentation, previous presentation, had actually shown the baseline results from 2-3 papers. So how do you evaluate there versus what is currently happening in yours as well as in what is currently happening, please?
Oh, okay. So what I did for my perspective was like many works in the literature use pretty common models such as decision trees, support vector machines, k-nearest neighbors. So I got that models, maybe not exactly the same ones that they mentioned in the work, and I got some results. And I decided if I was gonna drop the model due to insufficient performance or I was gonna keep it. That was how I approached the project in general. Yeah.
Thank you very much.
Thank you.
Okay, thank you. I would like to now call upon the second presenter, which is Ndabuye Asengayo Gideon. Can you share your screen for the presentation?
Oh, thank you. Let me share my screen. Okay, is my screen visible and audio coming through?
Yes, you can start.
Okay, thank you. So, so this is my quick solution on the intrusion and vulnerability detection in SDNs. Okay, so a quick overview. Yes, we know that recently traditional networks have been changing towards SDNs, where mostly we have a central controller that oversees all the network traffic. So this actually introduces a single point of failure, which is prone to network discontinuity in various ways. One of the ways which can be these attacks. So we have data and we have machine learning techniques. So how can we build a solution that can actually help us know in advance whether these traffics are actually attempting to break our network? So the data was provided by ULA Communications. So it combines a portion of real users' data from the software-defined wireless area networking. So okay, so we have the data has primarily four types of flow data. So this is normal, distributed denial service attack, malware, and web-based. So this is where the thing starts to be kind of tricky. We have 4, but then these give us 15 specific classes. So more of that in a bit. So we had 1.7 samples for train and over 500K evaluation. Okay, so I had a few steps, a little over 5 steps in processing. So first, it's an obvious thing. Any data scientist would see that this is a classification problem with imbalanced data. So considering the fact that it was extracted from real users, I kind of hesitated to creating a balanced data set, which where I actually did try and error, but it kind of didn't seem to give me a real or a realistic outcome. And considering the fact that if it's going to be used in a real environment, this is the trend of how these particular attacks happen. So a model should never be, from my perspective, should never be trained to know that something like benign or bot kind of have the same particular rate of occurrence. So yeah, so the data was never resampled to deal with the imbalanced. So I just had to use other techniques. So there are a few missing values, I think, from a single column, which I replaced with experimentally with negative values, more of that in a bit. Then there were these normal obvious columns with no useful information, single unique values, and also the duplicates. But then on standardization, which standardization was vital because of the available missing negative values. I mean the negative values that the data had. So I did this discriminately, where I selected all the columns. These were actually the columns with the columns about the flags, the push or the acknowledge and so forth. So these were columns with only 2 values. So I factored them out when doing standardization using the standard scaler. So these had to make sure that the negative values that we actually created or left and didn't deal with in the original data should be actually dealt with using this technique. So as part of the challenge, we were supposed to create a baseline of at least 3 models. So I went for the boosting models, the most common one, like GBM, cut boost, and the hist gradient. So the data was actually huge in some way. So training should take, in most cases, would take for around 20 minutes or so. So cut boost has an inbuilt GPU support. So only for that, I use the GPU on Colab. So from the 78 features, we had only 70 left. And then a quick training for these 3 models. We have the results down here, where I evaluated on accuracy and the macro and weighted averages of precision and recall. So plug and play of these gradient boosting models, we can see that, okay, LGBM falls short when it comes to the macro averages of precision and recall. Hist boosting comes a little bit well, but then it's obvious that the cat boost did well. This is plug and play. No further techniques of training or so forth. So afterwards, I had to choose the cat boost classifier for the fact that it did well here, and then it has the GPU support so that the training time could be shorter than the rest. So this is the cat boost tuned and trained on certified K-fold. This is to make sure that we have the same distribution of the classes, and I have to activate an early stopping rounds of a third of the iteration count, which was 1500 to 500. So this technique actually brought this performance on each. Okay, this graph shows the performance on each of the classes, or in this case, the attack types of attacks. So we can see that we have a slight bit of a problem in infiltration in the last three web-based traffic flows. So more of that in a bit, but then the general accuracy is just 99.89. Okay, so here's the confusion matrix that shows us how the model confuses or correctly classifies particular classes. So we can see the three web attacks, which is what I said earlier, because we have only four primary attacks, which are then further divided into specific attacks. So you can expect a similar pattern in some way in various attacks. So the obvious one here is web attack, brute force, SQL injection, and cross-site scripting. The model kind of confused in one of them. So infiltration, the obvious fact was that we had a small count of the data samples from the original data set, and which is why they are just kind of mixed with the benign, which was the majority. So a discussion was about how do we get rid of this. So I was analyzing why the model kind of
30 seconds to finish.
Kind of mixed on these three web traffic flows. So we can see this is a 2D generated by principal component analysis. We can see that we have an overlap of these particular traffic flows, and so the infiltration is the same. So we can conclude that we need more data. We need more data to deal with that particular problem, so that the model can actually get a fine pattern between the web and the rest. So a quick wrap up, we have 90% baseline from gradient boosting models, which is good. Others wouldn't do this. So finally, 99.8 accuracy from the cat boost. And I think that's I'm out of time. So
I would like to request Evren to give a quick question, and then Vishnu.
Okay, Thomas. Hello, NWA. Thanks for this nice work. In your outcome of your report, you say that the cat boost, as far as I remember, cat boost with accelerated with GPU provides the best performance. Do you think that when you are required to use only CPU, do you think that the performance may change for the training and computation time perspective?
Yeah, the computation time, yes, changes. I tried that, and I don't get exactly why the performance kind of is never the same.
Mm-hmm.
I'm not sure yet how that actually works, but the performance slightly is different, but the training time is obviously different, because it was less like 3 minutes to train the cat boost on GPU, but around 30 something minutes on CPU. So you had to wait longer to get your results, so that you can see what to change. So it was better off using the GPU. So the difference in performance isn't significant, but yeah.
So you say that whether you are using CPU or GPU, the cat boost is the first one, you say, for the performance. That's right?
Yes.
Okay.
Yes.
Thanks.
Vishnu?
Yeah, I think this kind of this kind of class-based analysis is quite interesting. I don't have a specific question. It is the usage of cat boost is also I mean, kind of interesting as well. I don't have a specific question. Thank you.
Okay, thank you so much. Thank you, Gideon. Let's move to the next. Last but not least, we have Shamim to present for this problem statement. The floor is yours.
Greetings of the day. Am I audible?
Yes.
All right. All right. So first of all, thank you very much to ITU and OLAC for providing us such an opportunity to work on this intrusion detection on SDN environment problem. So this is my presentation outline. I'm going to start with introduction, our proposed solution, result discussion, ongoing works that we are doing, conclusion with our future target. So basically, the introduction, as Efren already mentioned, like the traditional network is currently being evolved and SDN is being introduced and widely adopted. So the centralized nature of SDN are vulnerable to potential attacks, and there's limited data set of real network data from the SDN environment. So we are lucky to have those kind of like exposure to real network data. So the data set, if you can see, it was like 1.78 million rows with 78 columns or features and 15 different classes of attacks. On the right side, if you can see, like there are 3 subgroups we have divided. One is these 4, which has more than 80,000 data. And the middle one is like more than 1,000 to like 6,000. And the minority class are very less. It can be as low as 6 samples for the heartbeat class. So what we have done is to address the class imbalance issue, we have kind of separated them into multiple groups, subset. And the goal is to identify different attacks based on their like although having their class distribution improper. Okay, so the next thing is our proposed methodology. First, we are subgrouping the data set, and then we are selecting the key features out of those 78. Ensemble model building, we have worked on stacking method, and then compared with 3 baseline models. And later on, we have measured the performance, like how's the F1 score for this imbalance data set. So for the data pre-processing and feature selection, first we have removed the missing or infinite values those were existing in the dataset, then combined upsampling and downsampling together. So let's say for B9, it was like more than 150K, so we reduced it to 80K. And then for the minority classes, if you can see on the right side, the original count, we have used smooth to upsample them, and this is the after smooth result. And there were like we tried multiple methods for feature selection. One is random forest with embedded method, and another one is PCA. So both were giving us roughly 30 features, and we handpicked 28 from them. Source and destination port number weren't much important, or what we figured out. And then we selected the random forest feature selection. So this is our ensemble methods architecture. The training data will be separated and will go to 3 different base learner, and the prediction result from those baseline learner will create another new training set, and a meta model will be trained. In our case, the meta model was random forest, and then the test data will be tested or validated on the final meta model, and here we get the final prediction. So in our result, our model achieved F1 score of 97.77%, with the requirement was to use 5-fold cross-validation. And that's why there were like bagging, boosting, blending, staking. We used staking for this one. And we for generalization, we also tried on a similar dataset, which one is CIC IDS. 2017 to check the model's robustness. And also here, if we can see the classification report to get a bird's eye view. So here the minority classes, they kind of struggle to get a good recall score. As there were less samples, and the majority classes, they perform fairly better. So this is one issue where we try to emphasize, but still we were lacking bit. And if we see in the bottom, like model training time, so these are the baselines. We see CNN and random forest from a very popular literature. It's a very heavy model. It takes a lot of time. In our case, the stacking method, although it takes a bit of time, but the accuracy and the result is much more better than the previous baseline. And if we can see the inference time on test sample per sample, it's also like it's not the best, but still better than the CNN and random forest. And as the performance is better than the standalone random forest and XGBoost. So after submitting the report, we are still working on the progress, as we are aiming to publish a paper on the ITU. Currently we are working on a hierarchical approach, and it takes heterogeneous models, and currently it has given like far more better result than the previous stacking. So if you can see, here are three baselines. In the hierarchical method, it's getting 91.16% recall or 92% F1 score, which is significantly better than the previous two. Here also on the right, you can see the class-wise. If for the minority classes, all the small classes, our proposed like hierarchical is getting good results. And also in the confusion matrix, if you compare from the like previous our current submitted version, so here on the minority classes, it's also getting fairly good result. On the left, it's the test set provided by ITU. This is the evaluation, and on the right, we also check the CIC IDS dataset, and it's also giving a good result, which can also be improved with like hyperparameter tuning and other methods. So about the future works, we are still we have some plan to work on few shot learning, as it is an anomaly detection. Zero day attacks are very popular, so zero shot or few shot learning, these are some areas where we can focus. And custom ensemble methods with voting mechanism to solve the imbalance issue. These are some literature paper we have gone through. We have some plan to like work on this one. So to conclude, like what we did in this competition. So if we compare from the baseline, our model accurately predicts the minority classes better than before, and the ensemble method is quite robust because it uses multiple weak learners and also a meta learner. So it's not biased, and there's less chance of overfitting as well. And we are using tree-based ensemble methods. They are easy to deploy on the hardware as well. And for XGBoost, let's say they have the capability of using multiple GPUs by default if there's available. So feature selection and data augmentation played a pivotal role in our experiments. And that's all for the timing. Thank you for your.
Thank you so much. I'd like to go into the Q&A. So Evren and then Vishnu.
Thank you, Thomas. Shamim, thanks for this nice work. In your future direction part, you say that you can use some additional fine-tuning techniques for threshold settings or parameters. So regarding your current work, what are the other tuning techniques that you may apply and that can be useful for this study?
All right. So for the stacking method, like we have used like some random like common parameters like for the decision trees, and also XGBoost, AdaBoost. So what we can do is we can use grid search CV, random search CV to find the best optimal parameters to optimize the model performance. And also like what we have found out, like to improvise the training time, the majority classes, if you can see, even this middle mid-range section. So if we reduce the number of samples in the training, significantly reduce, like let's say benign maybe 10,000, still we found very less degradation in the model accuracy. So these things can be improvised, and also the feature selection. I basically like tried with 12 or 14 or 16 features. The overall performance of model accuracy or F1 was very like insignificant difference, but the minority classes is where we have to like put more focus on.
Okay, thank you.
Thank you very much, Shamim, with the very comprehensive presentation again. I want to ask about inference latency. In your slide, you show CNN plus random forest as high inference latency. Can you explain that? Why?
All right. So this one we took from a literature and we replicated their architecture. So basically what they do is first they train the like data in a CNN model, and from the last layer, like they take the feature of the CNN model and then put like feed those feature as an input to the random forest model. So basically there are two different models are being trained, first CNN and then random forest. So that's why it's taking more time.
I mean, this is not training time, no? I mean, this is inference time.
Yeah, also in the inference, like when we are trying, we are seeing like the architecture is basically combining both, like using CNN and also the random forest, these two models. So that's why like when it's passing through the model, it's like getting taking more time to do the calculation and finding the result.
Great. Okay. Thank you.
Okay, thank you so much. Thank you everyone for presenting. Really, we had great presentation. And of course, unfortunately, we are running out of time, but we would love to see more of your work. So what can you do from now? Please update your GitHub repository, put your reports, your presentations, your code on the challenge GitHub. We would love to have all information in one central place. At the same point in time, extend your work to make a journal paper and publish in our special issue in the IT journal. Right now is the time that everyone has been waiting for, and it's the award ceremony time. And because we don't have so much time, I will try to be as quick as possible to finalize who are the winners. So let me, okay. So I will show the winners from my side so that we keep count. For the 2023 ITU ML Challenge, we have the first competition we are going to give network traffic scenario prediction challenge. And for this problem statement, I'm really excited for all the solutions that have been completed. They said you will receive $100. This is the problem statement. And the third Icari, which was created by congratulations. On the second place is $300, and is going to the team Hungarian by Alan. And for the first team, the first $500, and this is going to Belloc, Martin, only person in this team. So congratulations to everyone for your winning, for your great solutions that we have put us in this competition. Let's go to the next up is the intrusion and vulnerability software-defined network security. This is a recorded statement by ULAC, and the third team is going to receive $100 US, and the third best team is PASA-X and AWS Live Billion. Next up is the second team in the same problem and this MUIs and now for the first round, $500 US. So this is 500 Swiss francs for ITU and Study Lab. So for teams, this problem this month the first problem statement is $8. The second one is this one. I'm going to go to the last but please problem statement, but environment prediction, and on the third place at 206 francs, and this is M5G. Congratulations. Next, after 206 francs, second place. Congratulations. Last one, the winner of this problem statement, I followed by so congratulations to everyone for your solutions of being touch. And I would also like to thank everyone who participated in this problem statement. I also request ULAB, ZTE, and Family Park for making this activity. So once again, congratulations. And I would like to ask Vision for words before we close the session. So Vision, over to you.
All right, thank you very much. Yes, I think Thomas was bravely fighting the music. Yeah, thank you very much, colleagues. I would like to congratulate the winners, first of all, and then congratulations to the hosts themselves. You have really put up excellent problem statements. All three that we saw today, excellent problem statements. They had good data sets and baseline papers and research supported as well. So thank you much for putting up. I remember our initial discussions, and we are here today. That as itself is commitment and progress from the host and participants. The winning happens when you publish the data, publish the results. I mean, papers are to be written, and then that's the winning. Our prizes don't go to millions. You know that, right? So the winning happens when you share the knowledge and your paper gets published in the ITU journal. Please remember. With that, thank you very much to Thomas. Thomas, it was very difficult to fight the music, but you have done it very bravely. Thank you very much, Thomas, and everybody on our platform, Gino and others. Thank you very much for the support, and back to you, Thomas.
Thank you, everyone. So this is the end of our session. Thank you, and see you in the next session coming up soon. Thank you, and have a good day.
Thank you very much. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.